Hello students, here's our next lesson, and we're on notes number 54, and the lesson is called the Binomial Theorem, and we're breaking this down into a couple of days lessons. So remember that in our last lesson we talked about combinations, and in combinations order doesn't matter. You're finding the number of ways you can do something, and we did this specific problem where we found the combinations 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. And we got the numbers 1, 3, 3, and 1. Okay, well, now we're going to see how combinations tie into another concept. And you may have heard of Pascal's triangle before. Maybe in middle school you did some work with it. Well, what I want to show you now is a relationship between combinations and Pascal's triangle. So let's say you had 0, choose 0. There are no things to choose from and you choose nothing. How many ways are there to do that? 1. Remember, not doing something is considered a way. Let's say you had 1, choose 0. There's one thing and you're choosing nothing. There's one way to do that. And if you had 1, choose 1, there's one thing and you're choosing it. There's one way to do that. Let's say you have 2, choose 0. There are two things and you're choosing none of them. There's one way to do that. 2, choose 1. There are two things and you are choosing one of them. There are two ways to do that. And 2, choose 2. There are two things, you're choosing both of them. There's one way to do that. And we already saw from the last slide that we had 3, choose 0 is 1. 3, choose 1 is 3. 3, choose 2 is 3, and 3 choose 3 is 1. So we have 1, then we have 1, 1, then we have 1, 2, 1, and then we have 1, 3, 3, 1. So if you have any experience with Pascal's triangle, you realize that that's what we're forming here. And Pascal's triangle just keeps going infinitely far. There are rows and rows and rows below this. And we can talk about how we would generate a row from the previous row, and we can also talk about how we would generate a row without needing the previous row. So for now, let's talk about how we would generate the next row. So every row starts with a 1 and ends with a 1. And then what you do is you add the two numbers above to get the next number. So 1 plus 3 would give you 4, and then 3 plus 3 would give you 6, and then 3 plus 1 would give you 4. And notice the symmetry. Okay, you're always going to have the same numbers coming back down the other side. So the next row would be 1, and then 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, end with a 1, and so on and so on. We're not going to get to how you find an individual row or how you find an individual number in a row very much today, but I suppose if you were curious about that, think about it in terms of combinations. So the numbers I just wrote would be the combinations for 5. They would be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 6. So I suppose if you wanted to know the 10th row, you could do 10 choose 0, 10 choose 1, 10 choose 2, and so on, and you could find those numbers with your calculator. Okay, so Pascal's triangle has a ton of patterns in it. One pattern that stands out is the counting numbers here. And another pattern that you'll notice is the set of triangular numbers here. If you haven't heard of those, you have a 1, then you can make a triangle out of 3 dots, and then you can make a triangle out of 6 dots by adding another row of dots, and you can make a triangle out of 10 dots by taking what we just had and adding another row of dots, and so on. Those are called the triangular numbers. Tons and tons and tons of patterns in Pascal's triangle. It's really amazing. Okay, so it ties into algebra in this way. We're going to expand these binomials, and by expand I mean multiply it out to get rid of the parentheses. So if we have a plus b to the 0 power, it's just going to be 1, just like anything to the 0 power is 1, anything other than 0. If we have a plus b to the first power, it's just going to be a plus b, and I'm going to call that 1a plus 1b. You'll see where I'm going with this. If we have a plus b to the second power, then we need to FOIL, and we end up with a squared plus 2ab plus b squared, or shall I call it 1a squared plus 2ab plus 1b squared. So you can guess then what we're going to get when we multiply a plus b times itself 3 times. We can show it. A plus b times a plus b times a plus b. We already know if you multiply 2 of them together, you're going to get a squared plus 2ab plus b squared. And now if you multiply that by the other one, first I'm going to distribute the a and multiply it by all 3 terms, and I have a cubed plus 2ab plus ab squared. Then I'm going to take the b and multiply it by all 3 of them, and I have plus a squared b plus 2, whoops, you see what I did? I have to go back. Okay, I left something out of this. Sorry about that. Okay, going back, the first a I'm multiplying by all 3, so I get a cubed plus 2a squared b. I was wondering what was going on. Plus ab squared, and now I'm multiplying the b times all 3, and I have a squared b plus 2ab squared plus b cubed. Okay, now combining the like terms, for example, we have 2a squared b and we have 1a squared b, and also we have ab squared and we have 2ab squared. So altogether we have a cubed plus 3a squared b plus 3ab squared plus b cubed. So we have 1a cubed, 3a squared b, 3ab squared, and 1b cubed. Those are the numbers from Pascal's triangle. So we should be able to expand binomials without having to actually do all the multiplying if we can use some patterns. Pattern number 1, coefficients come from Pascal's triangle, and those numbers are combinations. Pattern number 2, the powers on a. We have a cubed, we have a to the second, we have a to the first, and we have a to the 0. Pattern number 3, powers on b. We have b to the 0, we have b to the first, we have b to the second, and we have b to the third. Okay, so we can expand other binomials using all of these patterns. So let's expand a plus b to the 4th. And no, I'm not going to multiply a plus b times a plus b times a plus b times a plus b. What I'm going to do is realize that in the 4th row of Pascal's triangle, right here, 1, 4, 6, 4, 1, those are the coefficients we're going to use. 1, 4, 6, 4, 1. And then the powers on a are going to descend. A to the 4th, a to the 3rd, a to the 2nd, a to the 1st, and a to the 0. And the powers on b are going to ascend. B to the 0, b to the 1st, b to the 2nd, b to the 3rd, and b to the 4th. And we're going to add all these together. And of course, you don't have to write the ones in your answer. Let's expand a plus 2 to the 4th. So we can apply all the same patterns. So we have 1, 4, 6, 4, 1. We have a to the 4th. We have a to the 3rd. We have a to the 2nd. We have a to the 1st. And we have a to the 0. And now we have, instead of b, we have 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and 2 to the 4th. And we're going to add all those terms together. So we have a to the 4th plus, now we multiply the 4 and the 2, so that would be 8. So 8a cubed plus, and we multiply the 6 and the 2 squared, so that would be 24. A squared plus, and we multiply the 4 and the 2 cubed, so 4 times 8 is 32. So 32a plus, and now we have 2 to the 4th, and that's 16. All right, now let's expand a minus b to the 5th. Well, what we've seen so far only works for plus, a plus b. So that's okay, we can change this to a plus something. What would it be adding? A plus the opposite of b. That's fine. Now from Pascal's triangle, the numbers we get for the 5th row are 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So we have 1a to the 5th and the opposite of b to the 0. Let's just do the a's. A to the 5th, a to the 4th, a to the 3rd, a to the 2nd, a to the 1st, and a to the 0. Okay, now we have the opposite of b to the 0, the opposite of b to the 1st, the opposite of b to the 2nd, the opposite of b to the 3rd, the opposite of b, let's run out of room at the end, to the 4th, and the opposite of b to the 5th. Add all those together and simplify. So we have a to the 5th. Now, because we have this opposite in here, we're going to call this minus 5a to the 4th b. And then in the next one, the negative squares, so it turns out to be positive, so we have plus 10a cubed b squared. But in the next one, because the negative is raised to the 3rd power, we still have a negative, so we have minus 10a squared b cubed. And in the next one, the negative is being raised to the 4th, so it will be positive 5ab to the 4th. And in the next one, the negative is being raised to the 5th, so it will be negative minus b to the 5th. So here we have another pattern we can combine with all of our other patterns, and that is if it is a binomial expansion of a difference, just alternate the signs. Minus sign, plus sign, minus sign, plus sign, minus sign. And you don't have to rewrite it like I did in the beginning. That was only because I didn't have the pattern yet. So don't worry about rewriting it, just do A is your first thing, B is your second thing, and alternate the signs as you go. Number 4, putting this all together, let's expand 3x minus y squared to the 3rd power. So row 3 of Pascal's triangle, we have 1, 3, 3, 1. Then we're going to have 3x cubed, 3x squared, 3x to the 1st, and 3x to the 0. Then we're going to have y squared to the 0, y squared to the 1st, y squared to the 2nd, and y squared to the 3rd. And because it's minus, we're going to alternate signs. Minus, plus, minus. And now we simplify. So in the first term, we need to cube the 3 as well as cubing the x. So we get 27x cubed minus. Now in the second term, we need to square the 3, so we get 9, and multiply that by 3, so we get 27x squared y squared plus. And in the next term, we need to multiply the 3 and the 3, so we get 9x times y to the 4th minus, and now we need to raise y squared to the 3rd, and that would give us y to the 6th. Easy peasy mac and cheesy. Okay, I think that's it for today's lesson. And excuse me, and I want to say that when you do these problems, they're going to have 2 different sets of directions. I think for number 20 it says use Pascal's triangle, and then I think for 24 through 28 it says use the binomial theorem. Well, you can just kind of ignore the difference in the directions. Just use Pascal's triangle. Just do exactly what we did in the examples. Use the numbers from Pascal's triangle, because we haven't really thoroughly talked about the binomial theorem yet. That's coming next time. Something to look forward to. I know you guys love theorems.